Hello, this is Hongo 605. This video is about the foundations and the modern trends in causal inference. My motivation of making this video is that some of my friends are in their training process, and in this week they will learn about hypothesis testing and causal inference. So they will receive the lectures from their India instructors. So the training period is very short, and the speed of the train is very fast. Due to that, I guess some of them will face the problem in understanding what is the basics, what is the key idea of hypothesis testing and causal inference. Therefore, I want to make this video to help them understanding the essence of causal inference. So more and more, for me, today's hypothesis testing is run in a totally wrong way, and I will explain why. So first, in order to understand the key concept of hypothesis testing, we need to know the philosophical origins of hypothesis testing. So because first we have the idea, and then some very smart mathematicians or statisticians, they can convert their idea. The idea is written by natural language, right? Then the idea might be written by written by Japanese, written by English, written by German, blah blah blah. So some of the brilliant mathematicians, they can convert the natural language into mathematical language in a very smart way. So we have to convert the natural language into mathematical language because mathematical language provides a framework that we can use to analyze this problem. For example, can you imagine calculate the calculus by natural language, so for example, by Japanese, without any mathematical symbols? So it is possible, but it is impossible for us to understand because there will be so many words, and that's the limitation of natural language. That's why we need to convert the natural language into mathematical language. But this conversion is not the most important part. The most important part is having the key concept written in natural language first. So, okay, let us talk about the philosophical origins of hypothesis testing. So the origins of hypothesis testing is given by a famous philosopher. His name is Karl Popper. So the key idea of his thinking is falsificationism. So to summarize the idea of falsificationism in English, it will be we cannot, the true theory, the true things cannot be proven. It can only be falsified. That means it can only be rejected. So nothing is true. We consider one proposition is true, That is only because we do not have enough evidence to prove it is false. Therefore, the key idea of Karl-Popper is scientific theories cannot be proven. So it can only be rejected. So therefore, based on the idea of Karl-Popper, so we have a null hypothesis, right? We have already learned about that. H0 is a null hypothesis. So we can only take two actions toward this H0. We can reject it, or we can fail to reject it. So this is the most important concept. So naturally, if we think naturally, the opposite way of reject is accept. But here, there does not exist an option of accept. The only opposite action of reject is fail to reject. We can never accept. So this is the philosophical foundations of modern hypothesis testing and causal inference. Nothing is true. We have to be skeptical toward everything. So based on Karl-Popper's idea, there are two mainstream of causal inference. The first approach is given by the famous statistician Fisher, who is the pioneer of modern statistics. So let us see the idea of Fisher. So Fisher's idea is that the process of science is the process of accumulating evidence to prove, to show, accumulate evidence to reject the null hypothesis. So for example, a police officer try to arrest the criminal. So in the modern law system, first, the police officer should assume the criminal to be innocent. Then the professor will try to collect evidence to reject the null hypothesis. The null hypothesis here is the criminal is innocent. Then the police officer has to collect evidence to show the criminal is not innocent. So here the professor wants to reject the null hypothesis. So this process of accumulating evidence is the key idea of Fisher. So for example, the criminal is very smart. So the criminal does not give many evidence to the police officer. So therefore, the police officer could not collect enough evidence to make the criminal be guilty. However, it does not mean the criminal is innocent. The only reason is that the police officer does not have enough evidence to show the criminal is guilty at this moment. But our police officer is very hardworking. He keeps search for evidence for over 20 years, over 30 years. Finally, the accumulated evidence is enough to show the criminal is guilty. Then at that moment, the police officer will have enough evidence to reject the null hypothesis, which is the criminal is innocent. And that's the key process of Fisher's idea. So the Fisher's idea is evidence-based hypothesis testing. So how to translate the Fisher's idea into mathematical language? We have to use probability as our tool. So Fisher's idea is use one kind of probability as a p-value. So remember that this is the key, this is the true concept of a p-value. The p-value definition on Lex is totally wrong. It is a common misunderstanding because it is easy to teach students in that definition, but it is wrong. So the true definition of p-value is the probability of observing the current data, assuming H0 is true. The probability of observing current data assuming H0 is true. So therefore, this probability is a conditional probability. So the p-value in mathematical language, p-value equals to this conditional probability. So the condition is H0 is true. And the former part is, the former event is observing current data. So therefore, the formal definition of p-value is the probability of observing current data when H0 is true. So therefore, the evidence is current data. The evidence is current data. And the current data is the only evidence we have. Therefore, when the p-value is small, then it means the probability of observing current data when H0 is true is very small. That means the evidence is strong. We have strong evidence. We have strong evidence to reject H0. And on the other hand, when p-value is large, that means the evidence we have is not strong enough. We have weak evidence. Therefore, that is the key idea of Fisher's idea. So remember that Fisher will never give a threshold of a p-value. So no threshold for p-value. In the next course, we have learned that when p-value is, for example, smaller than 0.05, then we tell it is significant, and we can reject H0. And when p-value is larger than 0.05, then we cannot reject H0. So 0.05 is the threshold. We learned it on Lex, but remember, it is not true. So the feature will never give a threshold for p-value. Why? That is because when p-value is small, the only reason is the current evidence is not strong enough. It cannot say we can reject H0. We cannot reject H0. When we collect the sample for another time, or maybe in the future, we will have stronger evidence to reject H0. So the whole process is the process of accumulating evidence. It's not the process of a single decision making. So the key problem of the modern causal inference is that it turns a process of accumulating evidence into a single decision making. So therefore, the key idea is accumulation is true, and the single decision making, we cannot do that. Especially we cannot conduct the single decision making by p-value. However, many teachers and many scientists, they do that today, and this action is called as p-hacking. P-hacking is not a good idea. So for now, we have talked about one mainstream of hypothesis testing, which is based on the idea of feature. And now we are going to talk about the second concept, or second mainstream of hypothesis testing. That is the framework of Neyman and Pearson. Neyman-Pearson. So the framework of Neyman-Pearson is totally different from the framework of Fisher. The key concept of Neyman-Pearson's framework is they want to find industrialized decision rules. So they want to find the decision rules. So Neyman and Pearson's attitude toward the science is that the science is about designing decision rules that perform well under repeated experiments. So the key idea is they want to find a decision rules that perform good under repeated experiments. So therefore, their idea is quite industrialized. For example, in a factory, so the owner of the factory will, of course, want to set a set of rules that works very well under the everyday's production to maximize the factory's product level, or maximize the profit of this factory. So how to design these decision rules? We need to have a criteria, and the criteria of Neyman and Pearson is they want to control the long-run error rates, right? This idea is also quite industrialized. So, for example, if we are stable, and we need to control the long run error rate, because that is shows the quality of our products, right? So the aim is to control long run error rates. Okay, now we have our idea written in natural language, that is English. And now we want to translate this idea into mathematical language to analyze it. How? We have two things to do. First, we need to define what is error rate. That is the first step. And the second step is we need to think about how to control it. Okay, this thinking process is quite classical. First, we define a criteria, then we try to control that criteria. So that is the core philosophy of Neyman-Pearson's framework. So first, we will see Neyman and Pearson's process of defining the error rates. So they gave two types of error. Type 1 error, which is noted by alpha, and the type 2 error, which is noted by beta. So there are two events. So the type 1 error event is that we reject H0 when H0 is true. And the definition of a type 2 error event is that we fail to reject H0 when H0 is false. So let us talk about the definition again. So the type 1 error is that when H0 is true, what we should do is to not to reject it, but we reject it wrongly. And that means we kill a nice guy, right? This guy is not guilty, but we kill him. That is the type 1 error. And the definition of type 2 error is that we fail to reject H0 when H0 is false. So when H0 is false, what we should do is to reject H0. But we fail to reject it. That means we let a bad man go away. So that is the type 2 error, which is noted by beta. So now we have two events, alpha and beta. And now we want to translate the events into error rate. The natural idea is that we use the probability of alpha and the probability of beta to illustrate the long run error rates of type 1 error and type 2 error. And now we want to control the alpha and the beta. So we want the probability alpha, P alpha, to be as small as possible, right? Because we want type 1 error is an error, and we want to make this error rate as low as possible. So we want to control the P alpha to be as low as possible. And at the same time, we have to ensure that 1 minus P beta be as large as possible. So why? Because the probability of beta denotes the probability of failing to reject H0 when H0 is false. Then 1 minus beta will equals to the probability of successfully reject 0 when H0 is false. And that is the only thing we want to do, right? Remember the concept of hypothesis testing. The only thing we want to do is successfully reject H0 when H0 is false. So therefore, the important idea is we want to make this 1 minus P beta be as large as possible. So this 1 minus beta, we call it as the power, because it denotes the power of this of our data. So let us see the procedure of the decision rules of Neyman-Pearson. For the first step, we should set alpha as 0.05 or 0.10 or 0.01 before observing the data. So we have to set it before observing the data. After we observe the data, there is no meaning for set alpha, because, for example, we are unstable again. Then we cannot set the error rate after production, right? So if we set the error rate after production, then all products can be good products. But that is some kind of cheating, right? So we have to set alpha before seeing the data. And for the second step, we choose a test statistic. In our course, it will be a T statistic or blah blah blah. There are many different test statistics. For the third step, we will determine the critical zone or the critical region. Based on the alpha we set. So we can determine the critical region because we have the law of large number and the central limit theorem. And so therefore the distribution, we can have the distribution of our test statistics. For example, when we use the T statistic, then the T statistic follows the student T distribution. And actually, this kind of assumption is not good enough, in my view. So that's why, because when we determine the critical region, we have already assumed the probability distribution of the test statistics. However, in reality, the central limit theorem and the law of large numbers do not work so well, especially for the small sample size. That is the example in the on the next course. So for the final step, we can make the decision. So we can, if our parameter is located in the critical zone, then we can reject the H0. Or on the other hand, it cannot reject the H0. So what is the important thing is, in the Neyman-Pearson's process, the only tool we use is alpha and beta. So we want to, after controlling the alpha, we want to make 1 minus beta be as large as possible, because 1 minus beta denotes the maximum power of our of this Neyman-Pearson procedure. So there does not exist a p-value in the Neyman-Pearson procedure. What I want to say is, p-value and alpha beta is a totally different. They have totally different foundations, and we cannot mix it. That's what I want to say. But currently, many people, they just set the p-value as 0.05, and so they calculated the p-value, and they compared the p-value with this significant level. So if p-value is smaller than alpha, then we said it is significant. When p-value is larger than alpha, then we said it is not significant. No. This idea is totally wrong. So we cannot mix the p-value and the alpha beta, because the idea behind them are completely different and separated. So actually, the fighting between Fisher and Neyman-Pearson remains for nearly 30 years. So they fight a lot, and we cannot mix it. And then the question comes, why in current college and current especially econometrics process, what we do is the hybrid between Fisher and Neyman-Pearson. And that is because the only thing it is because they have two reasons. First is it is easy to teach and understand. So teachers can summarize the procedure of hypothesis testing into calculate p-value, into set alpha, the significance level, then calculate p-value, then compare the p-value and alpha. So this procedure is much more easier, and it is easy. It's much easier. It's easy to consider. So that's the one incentive for this mixture, and another incentive is p-hacking. So that is a very evil idea, especially p-value are abused in biostatistics, in biology, and in economics. So that is why I think these two, biology and econometrics, they are some kind of bullshit, because they are doing the p-hacking in all the time. And furthermore, p-value, p is a probability. Therefore, mathematically speaking, when sample size is large enough, when sample size n is become larger and larger, then the p-value will become smaller and smaller. So that is because the p-value is the function of function size. It's a monotonically increasing function of sample size. So when sample size becomes larger, then p-value is a monotonically increasing function, a decreasing function of sample size. So when sample size becomes larger, the p-value will become smaller and smaller. That's why the how small the p-value is does not make any sense, especially in the biological case. So when they test the DNA or the genes, the sample size is millions and trillions of sample size. When the sample size becomes millions and trillions level, their p-value are so small, and the p-value does not make sense anymore. And not only me notice this, so many statisticians or mathematicians, they notice that. And that's why the current decision-making process are not making by the hypothesis testing anymore. And finally, that will compose the last part of this video. So I want to introduce the modern trends in causal inference now. So how the frontier of today's search, they do causal inference. So the first movement is that instead of focus on p-value, we focus on confidence intervals. So the formal definition and of confidence intervals, I will explain it in another video, because it is another common misunderstanding. So what we can say now is by using confidence intervals, so we can look at the comparatively large intervals of confidence. Therefore, it provides the effect size and uncertainty. So the existence of uncertainty is very, very important. That is because the existence of uncertainty provides that the hypothesis testing is not a single decision making. Why? Because when we are not 100% sure, then we cannot make the decision on one shot. We have to observe it in a long run. And that is close to the idea of Fisher, right? So one modern trend is that we focus on confidence intervals. And the second trend is that we focus on the effect size. The effect size means we focus on the how large the effect is. So instead of just looking at the p-value is larger or smaller than 0.05. So when the absolute value of the parameter is very low, very small, then the p-value does not make any sense. Even though we have a very small p-value, such as 0.00001, but the absolute value of the parameter is 0.00002, then the effect of this parameter is so small that it does not make sense anymore. And the next trend is about the Bayesian methods. So this is the most complicated but the most important source of statistics. Actually, all the modern statistics are based on the they are based on the Bayesian framework. So we have to mention that the idea of Fisher and the idea of Neyman Pearson, although they are different, but they are all belongs to the frequency school. The idea of a frequency school is that the parameters is a constant level. It does not change by time. So parameter does not change by time. Therefore, we can repeat the experiments. We can accumulate the evidence to determine whether we can reject the null hypothesis or we cannot reject null hypothesis. So the prerequisite is the beta is not changed. It is a constant variable. So however, that is the limitations of the currency school. So in the idea of a Bayesian school, so zeta is a random variable. So it has the pre-probability and the pre-real probability and the post-real probability. So what we do is we want to maximize the post-real probability after observing the data. So in future videos, I want to explain more about the Bayesian methods. But the only thing we need to know is the causal inference we learn now is uncorrelated with Bayesian's methods, and the Bayesian's method is the mainstream of today's statistical inference. Okay, so that's all I want to say. So I hope this video can enhance our understanding about hypothesis testing and causal inference, and can eliminate some common misunderstandings toward the hypothesis testing and causal inference. Thank you.